Uh, Good morning, everyone. I'm glad to have this opportunity on behalf of all authors from Hunan University to present the research today. And for this paper, all authors of Songyue Wang and Professor Lu Deng and Dr. Jingjing and Mi Liu and Rui Cao from Hunan University. By the way, I'm Wei Chen from University College London. Today, the presentation is about automatic quality inspection of Rebar spacing using vision-based deep learning with RGB deep camera. Okay. The work includes 4 aspects: research background, and will follow by the methodology. And then we will show the experiments and results. Finally, we'll show the conclusions. As we know, the rebar engineering is very important for the structure safety. And this, as we can see from the picture, if the rebar structure system collapses during the construction, it will cause a very dangerous consequence. For example, the skill will be delayed and the construction worker may be died and some big financial loss. And as we know, in many countries, we have the practice of building code for the rebar spacing. And usually the rebar spacings must be larger than around 20 millimeters. And currently in the construction process, we have to inspect the rebar spacing during the construction. And the current work process, we still done this by manual. We can see we manually to inspect the process and to check the quality. And at the same time, we also to check the rebar console's work to make sure it's acceptable. However, those current process has the drawbacks. The manual inspection is time-consuming, is cumbersome, and also error-prone. And for the second process, sometimes if this rebar spacing is not acceptable, we have to rework, and the construction will be delayed. And the disaster consequence, the people may die. That's very important for us to make sure the rebar engineering is correct. Okay. Let's see which method we may use for the rebar spacing. And currently there are 2 methods we may use. One is the model-based method. Another one is image-based method. For the model-based method for rebar space inspection, currently, I think many research already know that we can use the LiDAR scanner to scan the rebar on the construction site. One is the handheld mobile LiDAR scanner, so we can scan this. Work around this construction site. Another one is the static scanner. And we can also scan this from different angles. It depends on where you put the scanner. But for this process, it still has the limitation. For example, the data collection is time-consuming, and the computational process is very complex. And in addition, this process is not real-time, and it's not suitable for construction site. So, and at the same time, the laser scanner, we scan for the 3D, right? We get the 3D points, but for the rebar spacing, usually we need to make sure we need to convert this to a plan to check the space for the 2 rebars. So it's not suitable for us. And the second method is image-based method for rebar spacing inspection. This method has advantages. For example, it's very convenient to option. And we can get the real-time data to suitable for the construction site. So we get the 2 points, determine the distance for the different rebar. But there are still some problem we need to address. Like for example, there are 2 layers rebar, and the dark blue is show the top view, and the light blue show the second layer on the below view. You can see the green point show the crossing points, but the red points is the pseudo points. We don't need that, but it's ignoring for us to recognize the space between 2 rebars. So you can see the feature similarities of multi-layer rebar construction affects the vision-based rebar spacing inspection. All right, it's missed one. So let's see how we improve this process using our own methods. There are 3 steps. The first one is the single layer rebar segmentation model, and followed by is the rebar cross-point recognition and localization module. And the last one is automatic inspection of rebar spacing module. Let's see how we process this step by step. In the first module, they plant the fitting to flatten the background rebars, and then they get the rotate the point plan, and then they expand the display pixel and move to the second step, use the YOLO weight position recognition, and they find the pixel coordinates of the rebar cross points. And then afterwards is the coordination converse and the 3-dimension spatial coordination after they get that, and they get the adjunct point spacing detection in the third steps, and then they can check to assess the rebar spacing. That's for the whole process. And let's go deeper to see how they process this. In the first one, before, some research already done the similar work. For example, the Jing applied a deep assistant techniques. This one, they ignore the pixel beyond a certain deep threshold, but they fix the distance from the RGB deep camera to the rebar place. So you have to put the camera in a fixed place, get the fixed distance. So that's the drawbacks for that method. So we want to improve this one, and we want to improve this one. So how can we improve this in this research? Let's see. Okay. The first step is they get the RGB depth camera to capture the color and the depth images, and then they generate the point clouds and apply the pass-through filters for the denoising. And then they plant the filtering and identify the target rebar layer. So they, for example, there are 2 layers. They identify 1 layer for the next step, and then there are the angles, right? There are the angles. So the line fitting to determine the minimum angle between the rebar lines and the XA planes. And afterward, they convert the angle to the horizontal and the vertical, and to get the rebar layer on an imager to perform the rotation. And afterwards, the dilation canal operation to expand the displays of the rebar pixel. And the output from the first steps will be the input for the next step. And for the rebar cross-point recognition, in this work, they choose the YOLO weight pose for the key point detection. And you can see they use the pixel coordination to get the they use the YOLO V8 position to get the pixel coordination of the rebar cross points, as we can see on the upper figure. And then they input the depth images and to using the camera intrinsic transformation matrix to get the spatial coordination of the rebar cross points. That's for the second step. And then for the automatic inspection of rebar spacing module, we can see the distance for these 2 distance is not correct for us. It's not useful, and it's also a noise. So we have to find the distance from M to N1. That's that's our target. So it means they must to identify this distance in this rectangular, and the coordination of point I to point M must be extremely to identify, and they also identify the other pixel dimension to meet the requirements. Okay. Afterwards, for this research, they did the experiments for each steps. first one is verifying the segmentation efforts, effects at different distance and diameters. And the second experiment is to find the segmentation efforts, effects at different rotation angle. And the last one, they validated the Rebar cross-point recognition and the localization model, aligning with the automatic spacing inspection modules. So they validated this. You can see in the first experiment, they found that the segmentation efforts from different distance. You can see from the upper to lower, the distance increase. So we can see the segmentation performance decrease. And for this one, for the right side, you can see if the dimension of the rebar is thicker, so we can identify the rebar clearly. But if the rebar becomes thinner, so it's not easy to identify. So that's the finding for the first experiment. For the second one, you can see they have to rotate the different angle and to make sure the rebar plays to the horizontal and the vertical clearly. Okay, for this experiment, we can find this for different rotation angles and diameters. The rebar aligns roughly panel to the X and Y, and they dominating the effectiveness in maintain the accuracy despite changes in different orientation. For the third experiment, we can see the input. We use the automatic quality inspection for rebar spacing, so we can get the output. This table to shows the error. The average error is 2.65 millimeters, so it's acceptable for this for the quality checking. And this one is a video to show the case study applying the proposed method. And see, it can be automatically to check the rebar, the cross points, and also to automatically calculate the distance between the different cross points. Yep. So we validate this method to see the result is acceptable. And yeah, finally, let's move to the conclusion. In this research, they developed novel method for the automatic quality inspection of rebar spacing. And it's worth to highlight this method didn't require the fixing the camera distance and the angle. So it's very useful for us to to apply this method in the construction site. And they identify the adjacent rebar cross point, so they can facilitate the automatic measurement about rebar spacing. And they also validate through the results, the different experiment testing on the different physical entities. Okay. And yeah, even though for this work there are some limitations, the camera view. The first limitation is the camera view. The camera view restricts each capture to only a local regions of the rebar layers. And the second limitation is they adopted a layer by layer approach now. And so in the future, they have to plan to refine this methodology to enhance acceptance of the inspection process. And they also would like to validate the method in more complex scenarios. For example, in different construction sites and the prefabrication plants to make sure this method is more robust. Okay. That's the whole work they have done, and thank you for your listening. If you have any questions, you can reach out to the first author, Songyue Wang from Hunan University, and Professor Lu Deng's team. Yeah, thank you.